All right, let's just jump right in. Something huge, I mean truly monumental, just happened in the world of technology. It's a fundamental shift that could literally rewrite our future. And the craziest part? It feels like it went completely under the radar for almost everyone. But we're going to talk about it right now.
I mean, just let that sink in for a minute. We're talking about the smartest people in one of the most complex fields on the planet. They hit a wall, a roadblock that the entire industry basically agreed was insurmountable. And then, someone just solved it.
So what exactly was this impossible problem? And maybe more importantly for all of us, why does solving it feel like we just hit the fast-forward button on the future, maybe by as much as a decade? That's what we're going to unpack right now.
Okay, so to really get why this solution is such a massive deal, first we have to appreciate the sheer, mind-bending difficulty of the problem they were up against. We've got to look at the very foundation of quantum computing and just how unbelievably fragile it is.
It all comes down to this one word: decoherence. You can think of it as the ultimate villain in the quantum story. The basic building blocks of a quantum computer, the qubits, are, well, they're divas. They are so incredibly sensitive that the slightest little thing, a stray bit of heat, a tiny vibration, literally any noise from the outside world, and poof, the information they're holding just vanishes into thin air.
And this is honestly the best way to picture it. It's not just hard. It's a constant, violent battle against chaos. You're fighting physics itself just to keep that qubit stable for a fraction of a second. And that fragility, right there, has been the giant wall stopping us from building truly powerful, large-scale quantum computers.
So, for years, scientists have had this idea, right? A theoretical hero qubit that could solve this whole fragility mess. But this hero came with a catch. A huge, frustrating, almost cruel paradox that seemed to make it useless.
The idea was called the Majorana Qubit, and it's brilliant. Instead of putting all your precious quantum information in one super delicate spot, what if you could kind of spread it out, smear it across two different locations that are intrinsically linked? That way, a random bit of noise hitting one spot doesn't matter. To wreck the data, you'd have to disturb both spots in the exact same way at the exact same time. And that is way, way harder for the universe to do by accident.
Yep, safe boxes. It's the perfect metaphor. The information is locked up tight, naturally shielded from the chaotic outside world. It's inherently stable. Awesome, right? Except, here comes that massive problem I mentioned.
And here it is, the very feature that made them super safe. The fact that the information isn't in one single place also made them, well, unreadable. You can't just look at one spot to see the data because it's not there. It's like you built the world's greatest, most secure vault, but you forgot to build a door. The treasure is inside, for sure, but you have absolutely no way to get it out.
But this is the moment everything changes. A team of researchers finally figured out how to pick the lock. They found a way to open that uncrackable quantum safe. And this, my friends, is the breakthrough.
And look, this isn't some fringe claim from a random paper. We are talking about top-tier institutions, Delft University and the Madrid Institute of Material Science. We're talking about a publication in the journal Nature, which is about as legit as it gets. They didn't just think about it, they went into a lab and did it. They read the information inside a Majorana qubit for the first time in history. So how on earth did they do it? They came up with this incredibly clever end run around the problem. It's a technique called quantum capacitance. They realized, okay, we can't look at a single point. That's the whole issue. So instead, they developed a global probe that doesn't try to find the information, but instead measures the overall electrical state of the entire system all at once. It's like being able to tell if a box is heavy or light, without ever needing to look inside.
And the result? It's just staggering. They measured a coherence time, that's the useful lifespan of the quantum information, of over 1 millisecond. Now I know what you're thinking. A millisecond? That's nothing. But you have to understand, in the bizarre world of quantum mechanics, a millisecond is an absolute eternity.
And this chart really shows you what I'm talking about. Your typical conventional qubit, it holds on to its data for maybe a single microsecond. This new qubit, over 1,000 microseconds. That isn't a small improvement. That's a 1,000 times leap in stability. 1,000 times less fragile. It's just in a totally different league.
And I really want to hammer this point home. This was not a simulation. This wasn't some theory on a whiteboard. This was a real-world physical experiment in a lab that produced actual data. It proved that this impossible idea works. It actually works. What was once science fiction is now an engineering fact.
Okay, so what does this all mean for us? Why does it matter? It matters because when a theoretical idea gets proven in the real world, it stops being a what if and it starts being a when. This one experiment pulls the entire future of computing forward, maybe by a decade.
You see, for years, the entire industry has been stuck staring at this thing called the scaling wall. To build a really useful quantum computer, you need millions of qubits. But with the old, fragile ones, most of your qubits weren't even doing calculations. They were just there to correct the errors of all the other qubits. It was a nightmare. But now, with qubits that protect themselves, the wall has been breached. You can use your resources for actual computation. This breakthrough puts us on a brand new, radically faster timeline. For the next couple of years, other labs are going to jump on this, replicate it, and make it even better. Then, you're going to see the big tech companies start building actual processors with this new hardware. And by 2028, we're not talking about experiments anymore. We're talking about real-world applications that start to change everything.
And what kind of applications? Oh, just, the small stuff, like designing life-saving drugs atom by atom, creating revolutionary new materials for clean energy, building financial models that might actually predict the market, running climate simulations with terrifying accuracy. This is world-altering stuff, and that's not even the wildest part.
Because that last point on the list, AI training, that's where this all leads. This is the dot that I think a lot of people are missing. What we're witnessing isn't just one technological revolution, it's the moment when two of the most powerful forces we've ever created are about to collide. Just picture it. On one hand, you've got this exponential curve of AI, already shooting straight up, faster than anything we've ever seen. On the other, you have quantum computing, which has just smashed through its biggest barrier. It just went from theoretical to practical. And those two lines on the graph, they're about to intersect.
And make no mistake, quantum-powered AI isn't just a faster version of what we have. Today's AI is brilliant at finding patterns in huge piles of data. But a quantum AI, it will be able to solve problems that are fundamentally, mathematically impossible for any classical computer to solve. Simulating a new drug molecule, for instance, is a task that would take today's best supercomputer longer than the age of the universe. A quantum computer won't.
And that is the key takeaway here. Because of the breakthrough we just talked about, this convergence, this new era of computation, it's not some distant dream anymore. It is on our doorstep. We're talking about the next 3 to 5 years. The groundwork is being laid right now as we speak.
So I will leave you with this one question to think about. We are standing at the exact point in history where the two most powerful tools humanity has ever conceived are about to merge and amplify each other. So, what happens the day after they finally meet? What does that world even look like?